Right, welcome back. So today is week 10 of Sem 1 2021. So we are now so now we are going to revise what we need to do for the quiz on coming Monday. For the quiz, as you know, we are doing chapter 6 and 7, which will cover least squares and QR, as well as the various information. So for the quiz, you need to do at least the inverse of 2 by 2 matrix, determinant, QR decomposition, the economy decomposition of at least 3 by 3 matrix. There are many definitions that we need you to know, things like rank, invertibility, full rank, and so on. So we'll go through some of this information in today's revision. All right. Check. Yes, we're recording now. So I'm going to begin with one example and we'll work through it. So we begin with such an equation and then we're asking you to solve it. So as you know, in the first tutorial, you solve you solve these equations, and by solving, it means that we want to find x1 and x2 such that all the equations are satisfied. So then we say it's the solutions of the simultaneous equations. The word solution here means the values that will make all these equations true. And of course, in the initial part of your learning, we solve it in this way. We use Gaussian elimination and we put the augmented matrix in the following manner. 1, 1 represent the first equation. The coefficients of the first equations. 3 represents the value associated with the first equation. Minus 1, 1, and 1. And by now we know how to do Gaussian elimination. So what we do is we just take the second row and add it to the first row so that we can get this entry to be 0. Adding the second row to the first row is 2, and then we have 4. So in this representation, we already can find the solution because we can solve this equation. Is already obvious that it means 2x2 is equals to 4, implying x2 is equals to 2. And then we do back substitution. And we work it backwards because we are now taking this equation here, which is 1x1 plus 1x2 equals to 3. And since we already know what is x2, then it is 1x1 plus 2 equals to 3. x1 equals to 1. And then we have it, the answer, which is x is equals to x1, x2, which is equals to 1 and 2. So this is very, very easy to do. And we expect you to do this. Now, in tutorial 1, remember that the solution can exist. And if it exists, it's unique or infinite, or may not exist. So in this simple example, the answer is it exists and the solution is unique. Why? Because there is only one solution. So we call this the solution. And only this solution satisfies this equation. So it exists and it is unique. All right, so we need you to understand all this terminology in this course. Right, and then later on, we will give you extra equations so that then the problem will be the solution not can exist or may not exist, does not exist. Yeah, does not exist. Okay. So but we're not done with this equation, this problem yet. Let us take this And then write it in another way. We let A equals to 1 minus 1, 1, 1. And we let Y is equals to 3 and 1. So in fact, this guy is exactly the same problem as this guy in another form. This form, we are trying to solve it using the linear algebra approach, so that we will do AX equals to Y. And then now we are going to solve for the unknown X, which will be, of course, 1 and 2. So in this particular case, A is square, because I mean, it is a 2 by 2 matrix, and it is rank of, so you need to understand this terminology. What is the rank of A? And the rank of A, remember in previous lectures, we say it is the number of independent columns or row. And it is definitely, you know, the first column is not dependent on the second column, or the first row is not dependent on the second row. There's no way I can construct one from the other, or the linear combinations of the others. So this is rank 2, because there are 2 independent rows, there are 2 independent columns. The rank will always be the same. The rank row, rank column will always be the same. And the rank in this case is 2. Now, because this is also sometimes called full rank, because now my rank is 2. My rank is 2, and the number of rows, number of column, actually this rank achieve the maximum rank that it can get. So we call it a full rank matrix. In this particular case, we can find inverse, because A is square and A is full rank. We can find the inverse of A, because A is square and full rank. Now, if A is rectangle, you can forget about finding inverse, because inverse does not exist for rectangle matrix. But because A is square, so it satisfies the first condition. Second condition you need to satisfy is it must be full rank. So the question now comes, we need to solve the 2 by 2 matrix for the same problem. All right. So now I'm in page 3. Yeah. So I'm going to write A here. So A is equals to 1 minus 1, 1, 1. And the inverse of, so if I let the entries to be A, B, C, D, then the A inverse is equals to 1 over the determinant of A times, oh, I always forget this, DA minus B minus C. Okay, so therefore you need to know the determinant of A for a 2 by 2 matrix, and the determinant of A for 2 by 2 matrix is AD minus BC. So this was in your JC days. You need to do this. So now let's do it by brute force. So 1 over the determinant. The determinant is 1 minus 1. Okay, and then that little guy is DA. DA is 1, 1. And this is 1, and now this is becomes minus 1. So now the answer is 1 over 2, and we have this guy. Okay, so this is the A inverse. So remember our problem. We have this guy on the top here. Now I'm going to write. So with that, I can now do AX equals to Y, because A inverse exists. I pre-multiply both sides by A inverse. Now, because this guy reduces to the identity, so this is the second way I can find the solution of X. But I mean, it was like so much trouble, right, compared to Gaussian elimination. But for sanity check, you can do that. What is my Y? 3, 1. And what's my answer? Let's try. It's half. 3 Did I make a mistake, guys? 3 minus 1 is 2. 3 plus 1 is 4. Answer is equals to 1 and 2. So is that my correct answer? And I compare that with my Gaussian elimination, 1 and 2 on the top here. So my X either by Gaussian elimination or by the inverse is the same. Okay, the take-home message is this, guys. The take-home message is that in this particular case, we can solve it in two ways. And the reason why we can solve it in the second way is that because A is square and full rank, and then we can solve it this way. But we'll in the real world, we'll never find the inverse of a matrix because it's very, very expensive. Instead, we'll actually solve it in the third way, the QR decomposition. But maybe I think with this revision, you already can solve these kind of equations in two ways. All right, maybe I pause now and take questions. All right, now we're going to change the problem. We're going to change the problem from this to this. X1 plus X2 equals to 3. Oh no, not 3. I'm too lazy for 3. 1. And then X1 plus X2 equals to 2. I'm going to change the equations from this guy to the one on the right-hand side. And then you say that it looks almost the same. I mean, the first equation is the same, except 3 becomes 1. This guy becomes... But the very key thing that you need to notice for this example is the first equation adds up to 1. The second equation on the left-hand side looks like the first equation, adds up to 2. So something is terribly wrong here. You first tell me one thing, and then now you tell me another thing. So in this particular case, logically, you'll realize that there is no X1 and X2 that will satisfy both equations simultaneously. In our initial lectures, we show it geometrically that in this particular case, it is nothing but two lines never intersecting. Okay, two parallel lines in the world of R2, never intersecting. That's geometrically. Today, we will do it algebraically or using Gaussian elimination like what we are doing now to show you. Okay, so let's proceed. All right. So when we can reduce our equations to the matrix vector notation because it's more compact, and then we are getting these guys. And then of course we'll write the augmented matrix. And then we would reduce the augmented matrix to find the pivots to solve the problem. And basically it is row 2 minus row 1. And then we get this very funny equation, which is how we know that system of equation is, the word is inconsistent. And why inconsistent? Because you actually have two equations. One saying is equals to 1 and the other guy saying is equals to 2. When you perform row reduction, it reveals itself as this kind of, what do you call that? It shows itself as 0 equals to some value, not equals to 0. If you have 0 equals to 0, then you're perfectly fine. Okay, but here because you're, okay, yeah. So when would 0 equals to 0? So maybe I would just show you an example here just for fun of it. I have another equation that is equals to 1. Then this equation will be 0, 0, 0. Can you see? If I've given you an extra equation, 1, 1 equals to 1, 1x1 plus 1x2 equals to 1, then in the Gaussian elimination, when you do it this way, then the last row would reveal itself as 0, 0, 0. Okay, so, but hey, yeah, that's how you see it. All right, let's throw this guy away. And so we are we are here to now solve this problem. And this problem, now we realize that we cannot solve. So the solution does not exist. So if we are in tutorial 1, then we'll stop here and so if we say solution does not exist, okay, and then of course we want to try to do ax equals to y and solve by, we want to solve by the inverse, because we figure out that a is square, and we think that does the inverse exist? And then of course how do I check whether the inverse exists? And the inverse exists means that it must be square and all the column must be independent. And then, or it must have full rank, and then all, you have all these other invertible matrix theorem. So in this case, it is obvious that the first column and the second column are dependent. First row and the second row are identical, they are dependent. So this is only rank 1. Rank of the matrix in this example is 1 because there's only one independent column or row. So we are then left to say that this is not full rank, implying not full rank. What does full rank require? Because this is a 2 by 2 matrix, I need the full rank to be 2. But because it is only rank 1 and this is not maximum of 2, therefore it is not invertible. All right, so we cannot also solve for this. So the solution does not exist, we cannot solve for this. So of course, then we're left with our third thing, solve by the least squares. So in here, in chapter 7, we learn how to solve the problem by the least squares. So what is the least squares? Okay. Ax is equals to y. That's the problem we want to solve. But, okay. Okay, here is, but y does not lie in the column space of A. Why? Why did I say that statement? That very weird statement. You look at Y and you look at the columns of A, and there is no linear combinations of the columns of A that will make it 1, 2. How do I know that? All right, let's draw a few diagrams here. Let me draw 1, 1 now. So 1, 1 is here. This is 1 and this is 1. So this is the first column of A, as well as the second column of A. Any linear combinations of this column of A is nothing but here. It can only lie along this line. So the column space of A is nothing but this line. I can land anywhere along this line, but nowhere else, because all I can do is to have scalar multiplications and even linear combinations. I would just still land on this line. Now, where is Y? Y is 1, 2. So let me draw it in red color. This is Y. Let's call this U. U. Why? I mean, you look at this and it says that since I can only represent any values along this dotted line, I cannot represent Y because Y is not in the same space as U. So in our least square solutions or orthogonal projection, we project Y onto U. So that this red point here is the projection of y onto U. It is the closest point in the space of U that approximate y. Because if I choose it further away, then the error is longer. So now the error is orthogonal to my projection. This is the best that I can do. You can look at this as a right angle triangle problem. This is the long, this is the one, these two are the short side and this is the long side. Okay, so this length is shortest when it is perpendicular. All right, then you have to remember, of course, these equations. So this is a projection of y onto U is y dot U, U dot U times, so this is a scalar, and times U. So the interpretation of this is that I will find, if this is a scalar, I will find a scaled version of U. So I will land myself in this vector, and the scaled value is this guy, y dot U all divided by U dot U. Okay. Right. Now, so now the interpretation is clear why there is no solution in the linear algebra world. In the linear algebra world, it is this desired vector is not in the span of the column space of E. All right. So now, but we already see that we can find, but we can find a x hat such that ax hat equals to y hat and y minus y hat equals to the error vector. Where's y minus y hat? This vector in, maybe I should say in this purple color. This vector is E. E is equals to y minus y hat. Where is y hat? This is y hat. This vector here, I should draw in purple. This vector here is y hat. The y hat is the vector along U that is closest to y. E is the orthogonal error between, E is a vector that is orthogonal perpendicular to y hat. All right. So E, and here is the critical part, and the norm of E, the length of E is minimum. Okay, so the least square problem is a nice real world problem, because most of the time we can never find y in the column space of A. In machine learning, when you're in year 4, year 3, the size of A is typically, make a wild guess, guys, hundreds of K and tens of K, right? So these matrices are huge. Maybe you have a million entries, million rows, and tens of thousands variables. Or in fact, now Google are doing billions of rows and 10 or 100,000 of variables. That's the size of the problem you solve. Okay, so Oliver asked why we are not solving by the normal equation. So here we are going to solve by the least squares, which is the normal equation. Okay, and the normal equation basically means that you are not solving to find, you're not solving to find y, you are solving to find y hat. Okay, so when you cast the whole problem to the normal equation, you are nothing but solving y hat. All right, so let's try to understand this. Okay. Okay, why the word normal? Where did the word normal come from? Oh, but maybe let's proceed and see what we get first, so that we don't get stuck in the world of abstract thinking first. Let's be more concrete. All right. First is let's write the. Okay, let's try it concretely, guys, first, which is this problem, and then we cannot solve. So how to find the least squares? I will tell you the equations first. So what the least square solution first is to first generate the normal equations. And how do I do that? All right, let's try it again. We have, but since the equation, the solution does not exist, we try ax hat equals to y hat. And then we say E is equals to y minus y hat. And then is orthogonal to y hat. So implying ax dot E, so the dot product between this is equals to 0, because that's what it's saying. This is where's my mistake? Sorry. Let me pause this. Right. So I make a mistake here. The error is orthogonal to the columns of A. The columns of A shows you the span of what we can get in the column space of A. So the error is orthogonal to A. Where is it in this? This is at the error is orthogonal to the span of U. U is where we can land. The error is orthogonal to this, and this is a line because we only have one two-dimensional vector. Okay, but in the abstract setting, it is the whole column space of A. Now, the column space of A, when we want to show orthogonality, we can use this trick. We do the A transpose E, which is the same as saying the column space of A dotting with the error vector, right? So it's the same. And it is equals to 0 means that it is orthogonal. We replace E by y minus y hat. Y hat we replace by ax hat. So now we arrive to the famous equation, the normal equation. And now we always put this on the left-hand side and this guy on the right-hand side. Now we can solve for this equation. We can always solve for this equation. So this is called the normal equation, and we can always solve for, and that's very nice, solve for x hat. But remember, x hat is not the solution of ax equals to y. It's not this solution. This is what we wanted. But what we could best possibly achieve was only this guy. Okay, this x hat multiplying by the columns of A will give us y hat. This is what we have finally achieved. We have gotten y hat, not y. Okay, but we are happy with y hat because y hat is closest to y. So in this problem, then the problem would be the solving for this equation to get x hat. Now let's solve. So you need to know this for the quiz, how to solve a 2 by 2, 3 by 3 kind of problem. Okay, let's try. We are now in page number 5. Okay, I'll solve it for you now. So let me rewrite my equations. A equals to 1, 1, 1, 1. Y equals to 1, 2. I'm now going to do A transpose A x hat equals to A transpose Y. Now, the question is to use the normal equation, does A transpose A inverse exist? Okay. And here, unfortunately, in this particular example, it does not exist. Okay. A transpose A inverse does not exist. But never mind. We still can solve for x hat through this equation. Okay, once we have solved for x hat, we can put it there and then put the values there. Let me see. Okay, let's try to solve. All right. So the first thing you must realize is that A transpose A does not exist. A transpose A inverse does not exist. But let me convince you first. The transpose, I mean, this is a very strange matrix because it's all 1. So its transpose look like itself. So the answer is 2, 2, 2, 2. So this is A transpose A. So inverse does not exist. All right, never mind. What about A transpose Y? This is equals to 1 plus 2 is 3. 1 plus 2 is 3. So A transpose Y is 3, 3. Now, therefore, now we solve A transpose A x hat equals to 3, 3, which is A transpose Y. So you are saying that I can't solve for this, but of course now you can see it this way. And you put the augmented matrix and solve for the x, which you can, because what will happen now is that you have 2, 2, 3, you have 0, 0, 0. That's nice. So this is different. Even though the columns of A were dependent, but because pre-multiplying by A transpose on the left-hand side and A transpose on the right-hand side, it forces Y into the column space of A, and therefore it actually makes the equations consistent, and that's the key. So if you're wondering what magic did multiplying by A transpose did, was basically it brings Y into the column space of A, such that we now can solve for it this way. Okay, and then now of course you can solve, like you can say things like this is the pivot, and we have 2x2 plus 2x1 plus 2x2 equals to 3, and now therefore you can then write the parametric equation x1 and x2 is equals to 3 over 2 plus any constant that is this. Okay, so you need to learn how to do it this way, and this is the particular solution. And this is the homogeneous solution. All right, and then when we solve, what is our answer? Our answer is, the answer is it is, we can get it as 1.50 plus any constant. Oh no, minus. Okay. All right, it's okay. Right, now let's try. A is 1111 multiplying by 1.50. What we get? It is 1.5, 1.5. This is y hat. What was y? Y was 1, 2. So comparing y hat to y, I mean, it looks like it's quite close because the first element is off by 0.5, the second element is off by 0.5. Therefore, E is equals to y minus y hat is equals to 0.5 and minus 0.5. Okay. All right, so I'm going to show you how I'll do it in MATLAB, this thing. Okay, let's pull MATLAB up and then I'll answer some questions. Isn't it minus 1, 1? Which one? Let me see. Yeah, maybe I'll have mistake. It will be Oliver. Which one is what? Minus 1, 1? Did I make a mistake? The bottommost page, the homogeneous equation. Minus 1, 1. This one? The homogeneous equation. Let me see. Minus 1, 1. Let me check. Let me pause this. So I got a mistake here. So now I show you how I do my, what do you call that? Homogeneous equations. So I have these equations, 2x1 plus 2x2 equals to 3. And then to find the homogeneous equations, we do it this way. Okay, this is the process. So my mistake is here, minus 1 here, minus 1 here. And therefore, now and of course I can ignore the homogeneous equations because this doesn't affect the solutions at all. And then I set alpha to 0 and I solve for it this way. All right, but now, okay, you can practice by yourself. You can set different alphas, 1, 1, 1, 1. And for example, if I set alpha to be 1, then it will be minus 1, minus 1. So it will be 0.5 here. And what about this guy? This is alpha is 1. So this is 1. So what would I get, guys? I'll still get 1.5 on the top and 1.5 below. So choosing alpha equals to 1. So you will see that regardless of any alpha I do, the final equation y hat does not change. And that is why we call this the solution of the homogeneous equation, because changing the parameters here doesn't change the solutions at all. So Oliver now asks, if we solve via the normal equations, we take away the homogeneous equation. Okay, so this is a very advanced question. Okay, so let's do this. A equals to, so this you do not need to know, okay, guys, but y equals to, what's my y? 1, 2. Oh, so this is my A, 1, 1, 1, 1, and my y is 1, 2. So I'm going to show you the solution of x. X is equals to, if I just do it blindly, A transpose A inverse, actually it will fail here. Okay, so yeah, so we will fail here. So the way we want to do it is something called P inverse. Okay, but it's too advanced, not yet. In chapter 8 in SVD, we'll solve it this way. So it's P inverse of A times Y will give you X. And then you will see, hey, his X is 0.75, 0.75. So he have chosen a different alpha. But we just do A times X, his solution and mine would be the same, 1.5, 1.5. Okay, so his solution is 1.5, 1.5, but he have chosen a different X. And in the advanced course, you'll realize that we'll find the minimum length of X that still satisfy the equation. So this is not our problem here. All right. Okay, but last but not least, maybe I will just introduce you to the last problem, and you can try it at home. Okay, in the last problem we want to solve is the page number 5, number 6. And you need to know this for the quiz. 111, 112. This is A, and Y is 121. So again, the first part was originally our previous equation. 111 equals to 1111 equals to 2. So immediately you will realize that the system of equation is inconsistent. All right. So what do we do? Therefore, we can now, but now, this is interesting. We can solve for ATA inverse, because you look at this first column and the second column are not dependent. Therefore, A transpose A will form a square matrix with rank 2. Right? If you don't believe me, A transpose A, you figure out that it is this value, 3, 4, 4, 6. And the rank of this above guy is 2, and implying the inverse axis. Okay, so you go home and prove it to yourself. And because the inverse axis, therefore, X can be solved by, that famous equation, A transpose A minus 1, A transpose Y. So it can be solved by this way. Okay, so you go home and try to solve it this way. Now, if I want to ask you for the QR decomposition of A, implying QTQ equals to I, R equals to upper triangle, what I'm asking you to solve is, what I'm asking you to do is exactly this slide. All right, go to section 6.3.2, page number 9. And now you have columns of A as X. And now you are trying to form the QR decomposition. Q will be octonormal columns, meaning that the columns of Q, which we call U now, have length 1 and they're orthogonal against each other. So that's why we get Q transpose Q equals to identity. R will be the upper triangle. Okay, you have to figure out how to do this, but let me show you the answer now. All right, let's try. So I'm going to do this, and then I will show you in MATLAB. Of course, you have to do it by hand. A equals to 1, 1, 1, 1, 1, 2. So I got the A. QR equals to QR decomposition of A economy, because the second parameter is here. Getting my Q to be 3 by 2. Q transpose times Q equals to the identity. Okay, so you see that. However, Q times Q transpose is the projection matrix. All right, so you need to figure all this out. All right. Aaron asked me, is the error vector minus 0.05, 0.5? Okay, let me check. Yeah, you realize that I'm not very good with my math when it comes to this. Let me see the value. Y minus y hat. Y minus y hat is minus 0.5, 0.5. Is that right? Yep. Aaron? Okay. Oh, sorry, I didn't show you my screen. So Aaron got this right. Okay, so there's a mistake here. Okay. So the take-home message is that you need to go through all this, all the way up to QR and solve for this. And then finally, you need to, I mean, if you need to refresh, you need to get this done for at least a 3x3 matrix. Okay, maybe I'll pause here now and take questions.